Hi everyone! Today let's talk about session 6.3, the sampling distribution of the mean with sigma unknown, so we don't know the population standard deviation. Okay, so we know the population has mean mu, but however, we don't know the variance or the standard deviation. Okay? So in many real-life situations, the population standard deviation is unknown. When we don't know sigma, we will need to learn a new tool to help us to estimate the mu. Well, is it true that this standardized sample mean is normally distributed with mean 0 and the standard deviation is 1? But because now we don't know sigma, we try to replace sigma with the sample standard deviation s. And we know how to calculate the sample standard deviation, right? So given a sample, we can calculate its sample mean and we can calculate the sample standard deviation. Alright, so William Gossett invented the so-called student's t-distribution, where we can write the t equals to, you can see it's very similar to what we had before. The only difference is we replace sigma by s. So sigma is the population standard deviation, and we use the sample standard deviation to replace the sigma. Okay, so this is the t-distribution. So William Gossett was in charge of conducting experiments at the Guinness brewery to identify the best barley variety. At the time, the only available distribution was the standard normal distribution. But remember, the standard normal distribution, we require the number of sample is big, okay? But Gossett always performed experiments with small data sets, and he did not know sigma. Okay, so that's why he invented the t-distribution. Definition. A random variable x has the t-distribution with parameter nu. So this is not v, this is the Greek letter nu, okay? So it's like nu. If it has the PDF, so this is the PDF probability density function, then we know x has the t-distribution with the degree of freedom nu. So nu is called the degree of freedom. Okay, maybe you get scared with this fancy complicated PDF. Don't worry, we don't use PDF to calculate. We use CDF to calculate. Okay? All right. So that's the t-distribution. So here you can see the picture of the t-distribution. And here we also have the fact. If x has the t-distribution, then the mean of the t-distribution is 0. And the variance equals to nu over nu minus 2 for nu greater than 2. If nu is between 1 and 2, including 2, then the variance is actually infinity. Okay? So we're not going to prove the mean and variance for the t-distribution. So here is the formula. Okay, so we mark. You may have noticed the shape, the shape of the t-distribution. The overall shape of the t-distribution is very similar with the normal distribution. So both bell-shaped and symmetrical about the mean. Okay, and furthermore, actually, when the nu goes to infinity, when the degree of freedom goes to infinity, the t-distribution actually converge to the standard normal distribution. So that's why you can see this picture. The orange line indicates the nu equals to 1, okay? The purple line is the graph of t-distribution when the nu is 2, and then the blue line is when the nu is 5, and the black line is actually when nu goes to infinity. And when nu goes to infinity, the black line is actually the standard normal distribution. So this is the PDF, and then here you can see the CDF, and the CDF is increasing. You can see when nu goes to infinity, it actually converges, the t-distribution converges to the standard normal distribution. Do you still remember last class we talked about there are two convergence? We have convergence in probability and we have convergence in distribution. So convergence in probability, we have an example that's the law of large number. We have the sample mean, okay, converge to the population mean in probability. Okay, for the convergence in distribution, we also have the central limits theorem. Okay, we have the standardized sample mean converge to the standard normal distribution in distribution. Okay, so here we actually see another example of convergence in distribution. The t distribution converges to the standard normal distribution in distribution. Okay, this is convergence in distribution, and you can see we have the point-wide convergence. So that means we look at the CDF. So this is the CDF. We look at it for each values of x. You can see for each value of x, you can see those when we increase the nu, it actually converges to the CDF of the standard normal distribution. But however, the speed of the convergence are not the same. So here you can see, oh, this guy is actually quite equal, okay? So it converges faster, but here it converges slower. Here it converges and then here and here you can see this guy and this guy, the convergence speed are different. So convergence in distribution, we only know that it converges at each point. We have point-wise convergence. But however, the speed it converges at different points are different. Okay. So notation. T alpha. So T alpha equals to x, where P x greater equal to small x equals to alpha. So what is this guy? So this guy means that we draw the picture. So the picture of T alpha also looks like that. Okay, and the middle guy, we have 0. And what's T alpha? So T alpha is the x value such that the probability on the right-hand side of it is alpha. Okay, so then what's the probability on the left-hand side? Well, the probability on the left-hand side is then 1 minus alpha. So this is 1 minus alpha. So that's why we know that the CDF, so CDF of T alpha is actually 1 minus alpha. Okay, and what is T sub 1 minus alpha? Well, T sub 1 minus alpha means you draw the picture, you need on the right. Okay, you need on the right-hand side is 1 minus alpha. So this is 1 minus alpha. This is T 1 minus alpha. You can see what happened. Wow, this is actually negative of T sub alpha. Okay, so for the T distribution, I said we don't use the PDF to calculate. Oh, that is so complicated. So we don't use the PDF to calculate. And you don't need to memorize this formula. Okay, we use the CDF to calculate. So the CDF values are in table 4. Okay, all right. And let's compare with the standard normal distribution. So with the standard normal distribution, okay, we also have the similar analogy, right? We have, let me draw, it looks like more similar to that. So we have the standard normal distribution, the mean is also 0. And what's C alpha? C alpha is the x value such that the area on the right-hand side of that is alpha. So you can see T alpha and Z alpha, they're very similar concepts. Okay, just the distribution is different. Okay, so let me show you table 4. So we call that table 1 is the CDF values for binomial distribution. Table 2 are the CDF values for Poisson distribution. Table 3 are the CDF values for the standard normal distribution. And table 4 is going to be about the T distribution. However, However, the table is a little bit different. It's very different than what we had before. So what we had before is like we have the z values. We have the z values. Then we give with the z values we have the probability, right? But now, okay. So actually, this is the t alpha values. So this is a t alpha values. This is not like the CDF values. Okay, so what does that mean? Okay, so we know we have t distribution with the degree of freedom nu, okay? So nu is the parameter. So depending on the nu, we find the correct row. Let's say if nu equals 11, then we are at this row. What are those numbers means? Okay, let's look at this number. What does this number mean? This number is actually the t alpha values. So the t alpha values for alpha equals 0.025. What does that mean? Okay, we can draw a picture. So it means this is the t alpha value. So this is the, we know zeros here. So 2.201 is right here. So this is the t distribution with degree of freedom 11. Okay, so 2.201 is the t alpha value. It means the area of this guy is 0.025. So far, so good. So it's not giving us the CDF. This is not the CDF. However, we can see from this number, we know that the CDF of 2.201 why I keep writing the zero. So 2.201, the CDF values is going to be 1 minus this 0.025. So this is 0.975. Okay, so yeah, we're gonna do like a little bit more work because this is not a complete CDF values where you can give given any z values and then they give you a CDF values. This is not the case. This is t alpha values. Okay, so for a number, you know the alpha. The alpha is the area on the right hand side of the t alpha values. Okay, so this is special to the previous table we have learned. Okay, and also I hope you can look at the last row. You look at the last row, infinity. Do you remember what is when nu goes to infinity? What happened? Our t distribution converges to the standard normal distribution, convergence in distribution. So actually, this guy, the last row, corresponds to the z alpha values. Okay, so the last row actually corresponds to the z alpha values. Okay, so keep that in mind. Let's continue. So, okay, so what is the main use of the t distribution? Okay, we call the central limits theorem from last session. Okay, we have the IID data, and then we know the standardized sample mean is approximately to the standard normal distribution. Okay, so here, what happened if we don't know sigma, and what happened we don't have a large sample size? Okay, so this theorem takes care of that. So suppose x1, x2, x of n be the IID normal random variable. So IID means independent and identically distributed. Okay, and we also require it to be, it is normal. Okay, so this population is a normal population. Okay, suppose their IID normal random variable with mean mu and variance sigma squared. And here we don't know sigma, so we don't know it. And let x bar be 1 over n and the sum of xi. So this is the sample mean, okay? And let s squared be the sample variance. Then the t distribution equals to x bar minus mu over s over square root of n is actually a random variable having the t-distribution with the parameter nu equals to n minus 1. So this guy is actually a t-distribution with degree of freedom n minus 1. So far, so good, everybody? So I want to emphasize, because many students make this mistake. The degree of freedom is n minus 1. It's not n. It's n minus 1. Okay, so keep that in mind. So we might compare with the central limits theorem. We drop the assumptions that require the sigma to be finite number. So here we don't know sigma. It could be finite or it could be infinite. Okay, but we add the assumption that the population is normal. Okay, so we drop the assumption knowing the sigma, and here we add the assumption that the population is normal. Okay, and furthermore, when n goes to infinity, what happened? So when n goes to infinity, when we have a bigger sample size, okay, the t-distribution converges to the standard normal distribution. And it makes sense. It agrees with our central limits theorem, right? Remember central limits theorem, if n goes to infinity, our distribution actually converges to the standard normal distribution. And here it agrees with that. Okay, so in fact, let's look at the t-table. So t-table, you can see the degree of freedom, 1, 2, 3, 4, 5, 6. The highest is 29. So if you get the degree of freedom is greater or equal to 30, well then you can just use the standard normal distribution to calculate. Okay, so when n large, you can use the standard normal distribution to calculate. So what is large? Greater or equal to 30 is large. Okay, everybody? Yes. So greater or equal to 30, then you can use the standard normal distribution to calculate. Okay, you don't need to use the t-distribution. Yes. So that's why we can summarize our cases into 3 cases, okay? So first case, we have a large sample and we don't know sigma, okay? Sorry, we have a large sample and we know sigma. And then the standardized sample mean is the mean minus the mu over sigma over square root of n. This guy approximates to the standard normal distribution. Okay, and the second case, we have large n and we don't know sigma. In this case, we use the sample standard deviation to replace the sigma. And this guy is also approximately normal, so we can still use the standard normal distribution to calculate. And what is large n? Large n means greater or equal to 30. And third case, if we have a small n, so that means n is less than 30. But we have normal population. Okay, so in that case, we use the t-distribution to calculate. Okay, and we also use s because we don't know sigma. Okay, in this case, we have the t-distribution with degrees of freedom n minus 1. The degree of freedom is really important because it determines which row of the t-table we're going to use. Okay, so let's look at our examples. Example 1. Let T follow a t-distribution with nu degree of freedom is 8. Part 8. What is the probability that the absolute value of T is less than 2.306? Okay, so let's do it. Okay, so we have the t-distribution with degree of freedom 8. Part A, we're looking for the probability that the absolute value of the t is less than 2.306. Okay, let's see. We have the probability absolute value of t is less than 2.306. Okay, what does that mean? Well, this is the same as saying negative 2.306 is less than t is less than 2.306. Right? So far, so good, everybody? Okay, keep that in mind. Let's look at our t table. So let's look at our t table. Ooh. Okay, so degree of freedom 8. So we're looking at this row. 2.306. So that is, this is 2.306. Okay, and this is the corresponding alpha. Okay, so 2.306 corresponding alpha is 0.025. So what does that mean? It means that from the table, we know t alpha 0.0. Oh, I forgot. 0.025. 0.025 equals to 2.306. Okay, so we get t alpha values is 2.306, where alpha is 0.025. Okay, what does that mean? So let's draw the picture. T alpha is right here. So 2.306, and it means this guy is alpha. So alpha is 0.025. The probability on the right hand side of the number 2.306 is 0.025. Okay, what are we looking for? So we're looking for the probability between negative 2.306 and 2.306. So we are looking for this. Okay, so let's see here. This guy is 0.025, and do you see this guy and this guy? They are the same. Yes, they are the same. So this guy is also 0.025. Then what is the blue area? Well, the blue area is 1 minus the 2 copy of the orange area. So 1 minus 0.05 is 0.95. So far, so good, everybody. So this is the probability of the absolute value of t is less than 2.306. Alright, so that is part A. I strongly recommend you, when you look at the t alpha values from the table 4, please draw the picture. So draw this picture. So it can help us to figure out, okay, what's the probability, what's the t values. Okay? Part B, what is t.05 of 8? Okay, what's t.05 of 8? So let's look at our table. So that means alpha is 0.05. Oh, it's here. So the corresponding t alpha value is 1.860. So we can read from the table, this 1.860 is, we get this directly from the table. So far, so good, everybody? Alright, so I actually just add a part C, okay? It's like sometimes I'm teaching and I think of something new, okay, I want to add it and talk about more. So part C, what is t.99 of 8? Okay, so let's look at our table. Well, you want to find your alpha is 0.99, but do you have the alpha as 0.99? Oops, no. So you can see actually all the alpha values are less than equal to 0.1. So we don't have the alpha is 0.99. Okay, in that case, what do we do? Well, let's try to figure out what it means. Okay, so t.99. Okay, so we draw the picture. So think about it, 0.99 is so close to 0.1. So that means the area on the right-hand side of that number is large. So large means this number should be here. Okay, so, and we know this area is 0.99. Okay, if this area is 0.99, what is this little area? Well, that's 0.1, right? And because we know it's symmetric, okay, let me draw a better one. So we know it's symmetric. Okay, this guy is negative of this guy. So this guy is symmetric. So we know this is 0.1. So this is actually t.1. Sorry. Oh, this is 0.01. T alpha, my alpha is 0.01. Okay, so actually t.99 is negative t 0.01. The degree of freedom is 8. Okay, so now for this, I can find our table. Our table 0.01 is here. So that is 2.896. So that's why we get negative 2.896. Okay, so I strongly recommend you to draw the picture and then figure out, okay, what's that pieces? What's the area? What's the corresponding t values? All right, so that's part C. Okay, let's continue to look at example 2. All right, so a manufacturer of fuses claimed that with 20% overload, the fuses will blow in 12.4 minutes on average. A sample of 20 was subjected to a 20% overload. The time it took them to blow had a mean of 10.63 minutes and a standard deviation of 2.48 minutes. If we assume the data constitutes a random sample from a normal population, do they support the manufacturer's claim? Okay, so let's identify with the numbers. So 20% overload, this 20 is like a success, okay? So we don't need that. And it will blow in 12.4 minutes on the average. So this is actually the population mean, okay? That's mean. That's the manufacturer's claim that the fuse will blow the mean. The manufacturer claims that the population mean is 12.4, okay? And a sample of 20, so N is 20. Subject to a 20% overload, the time it took them to blow had a mean. So within this sample, the sample mean is 10.63 minutes. And the sample standard deviation, okay, still within the sample, we have 2.48 minutes. So if we assume the data constitutes a random sample from a normal population, do they support the manufacturer's claim? So here we can see the N. N is less than 30, so N is small. And because we have the normal population, we can use t distribution to calculate. Okay, so by our theorem, the t equals to x bar minus mu over sigma. So no, not sigma, we don't know sigma, over s over square root of n has the t distribution with degree of freedom n minus 1. Okay, so what does that mean? Okay, so we get the mean. Let's calculate. Okay, so that's why here we have degree. So this is what's the degree of freedom? So degree of freedom, our n is 20, so our degree of freedom is actually 19. Okay, so let's calculate our t values. So our x, so we know our sample mean is 10.63. Our claim population mean is 12.4. Over s is 2.48 over square root of n, square root of 20. Okay, so let's calculate what this is. So plug this in our calculator and we get the answers approximately by negative 3.19. What does that mean? We actually really want to know that. Okay, so we want to know that whether t has a big probability near negative 3.19. If the probability is big, then we say, oh, the data makes sense, okay, that's possible, so it supports the claim. But if the probability is so small, then, that's weird, the data is quite off, so the probability is small, maybe the manufacturer's claim is false, okay? So here we want to know whether t has a big probability near negative 3.19. Okay, so let's look at the table 4. For t degree of freedom 19. Okay, so let's look at these. So let's look at the table, the t table, table 4. So we have degree of freedom 19. So we're looking at this row. Okay, so let me copy this row into my Word documents. Okay, so here it is. Alright, so what does that mean? Wow, this picture tells us that if I draw the picture, okay, so here what it means. Okay, so this guy, this area is 0.10, and this t alpha value is 1.328. And the next number, the area is 0.05, and this t alpha value is 1.729. And then next, the area is 2.093, and then this is 0.025, and let's make it longer. So 0.01 to 0.539, and okay, what's the last one? Well, the last one, it means the probability on the right-hand side of that is 0.005, and this guy is 2.861. Remember, our picture is symmetric about the mean, the y-axis, okay, if there's a y-axis, like here. Then that's why on the other for our value negative 3.19 is actually on the left. Okay, so let's say this is negative 3.19. Okay, and then the next number, it corresponds to 2.861. So it means that the area here is actually equals to 0.005. So what do we get? We get the probability, okay, so this means the probability of t around negative 3.19 is actually less than equal to probability of t sorry, I forgot a negative here. Less than equal to negative 2.861, and the probability is 0.005. Wow, this is so small. It's almost unlikely to happen. Okay, so if the probability is so small, then we say, there's something wrong with the manufacturer's claim. Okay, so we answer it like, so the data do not support the manufacturer's claim. Okay, so that means the mean blowing time of his fuses with a 20% overload, okay, should be less than 12.4 minutes. How do we know less than? Okay, go back. His claim is 12.04 minutes, and our data, the mean is 10.63. 10.63 is less than 12.4. So we know that the mean should be less than 12.4 minutes. Okay, so actually this is an example of test of hypothesis, which we will talk about in chapter 7. Okay, in chapter 7, we will talk about like test of hypothesis given the manufacturer's claim. Does that make sense? Does the data support the claim or reject the claim? Okay, so that's it for chapter 6. And then in the next class, we will talk about chapter 7. Okay, so our course, we cover chapter 3, probability, chapter 4, discrete distribution, chapter 5, continuous distribution, chapter 6, sample and the relationship between sample and population, and also this introduce the t-distribution, okay, and chapter 7 is test of hypothesis, okay, and then we also will cover 11.1 regression line. Okay, that's our course. See you next time. Bye.